In this webinar, we're going to discuss PCIe Generation 5.0 SerDes test and analysis. We'll begin with a short discussion of Peripheral Component Interconnect Express, which is what PCIe stands for. We'll move to the challenges involved in transmitting non-return to zero, that standard baseband logic scheme that we've been using all our lives, at 32 gigatransfers per second. And then we'll compare PCIe Gen 4 and PCIe Gen 5 SerDes requirements. We're going to get into link training really heavily. This is the complicated part, so this is the part you really have to pay attention to. The transmitter phase lock loop bandwidth test is less complicated, especially after we've gotten through link training. Then we'll cover the jitter tolerance test, JTOL, and discuss base testing. And then we'll conclude with a description of the required test equipment features. PCIe is the leading interconnect I/O technology for hard drives, solid-state drives, graphics cards, Wi-Fi cards, and internal Ethernet connections. It consists of a set of fast, scalable, and reliable I/O standards for serial data transfer buses. It's scalable, it's fast, it's reliable. The physical layer, that is the PHY layer of PCIe, also supports the higher levels of several other protocols like NVMe, the non-volatile memory express, and SATA-E. This table shows the evolution of PCIe data rates. The fifth generation, PCIe 5.0, doubles the throughput from the previous generation, PCIe 4. Notice that PCIe distinguishes the raw transfer rate in gigatransfers per second from the linked data rate in gigabits per second. It's really nothing, just nomenclature. The key test equipment for SerDes testing consists of two pieces: a bit error rate tester and an oscilloscope. For the most complicated SerDes tests, the link equalization training, the Burt must emulate a reference SerDes. The pulse pattern generator, the PPG, and the error detector, ED, must interact with the device under test, the SerDes, at the PHY logical subblock level of the PCIe 5 protocol stack. In other words, both the Burt and the scope must have some protocol awareness, at least at the PHY layer. The biggest challenge in advancing from PCIe Gen 4 at 16 gigatransfers per second to PCIe Gen 5 at 32 gigatransfers per second is the ability to function with up to 36 decibels of loss at a bit error rate of 1 in 10 to the 12. To mitigate problems associated with loss, most of the other standards that operate in excess of 30 gigatransfers per second have adopted PAM4, the 4-level pulse amplitude modulation. But PCIe 5 continues to operate with the logic emulating baseband non-return to zero modulation scheme that uses, of course, high levels for logic 1s and low levels for logic 0s. It's widely anticipated that PCIe Generation 6 will make the switch. It operates at 64 gigatransfers per second, and it will operate with PAM4. With so much loss, a compliant PCIe Gen 5 post-equalization eye-opening can be as low as 10 millivolts. Such a tiny voltage swing requires extremely sensitive voltage slicers. Also, to accommodate long reaches of circuit board, retimers are required when loss exceeds 36 decibels or when the signal propagates through 2 or more connectors. In doubling the data rate from PCIe 4 to PCIe 5, the Standards Committee altered the compliance requirements as little as possible. To address signal degradation, more strict requirements in channel and connector loss and reflections have been implemented, and minor improvements in receiver and transmitter equalization have been made. But don't be fooled. The data rate has been doubled with no major innovations to compensate for the inevitable problems caused by steeper rise-fall times, narrower unit intervals, and greater insertion loss. Intersymbol interference, ISI, is caused by frequency-dependent channel loss. Each Fourier component of the signal experiences different levels of loss, causing bits to overlap and interfere. ISI is corrected in PCIe Generation 5 through an adaptive equalization scheme called link training. Link training involves communication between receiver and transmitter to optimize and coordinate the adjustable equalization parameters. Those parameters consist of the feed-forward equalizer taps at the transmitter, and at the receiver, the continuous time linear equalizer gain and the decision feedback equalizer taps. Feed-forward equalization at the transmitter is a generalization of the de-emphasis that we've used for many years, and it uses a shift register, as shown here, in order to pre-distort the waveform in a way that partially compensates for the distortion caused by the frequency response of the channel. Throughout its evolution, the PCIe specifications have set receiver performance requirements, but have never defined how receivers have to satisfy those requirements. Instead, like most standards, PCIe 5 defines a reference receiver, and that reference receiver has to have, it has clock recovery, continuous time linear equalization, and decision feedback equalization. We can think of the reference receiver as a reasonable receiver implementation that's defined for the purpose of evaluating transmitters. The Pcie Standard encompasses 3 interdependent specifications formulated to assure interoperability of SerDes and channels from different vendors. The Pcie base specification defines chip-level performance all the way up the protocol stack. It's a comprehensive document of over 1,000 pages. The CEM card electromechanical specification prescribes the minimum performance of devices at the add-in connector, and the test specification sets out rules for compliance testing. PCIe Gen 4 and PCIe Gen 5 have a great deal in common. Both use NRZ modulation, they both use 128B, 130B encoding, and they have the same 1 in a trillion bit error rate target. They also have the same connector pinout. The transmitter voltage requirement is unchanged. The jitter requirements are the same in both PCIe 4 and 5 as measured in unit intervals, but of course are proportionally tighter when measured in picoseconds. The distributed reference clock or common clock architecture was optional in PCIe Gen 4, but is now required in PCIe Gen 5. The transmitters use the same feed-forward equalization scheme and have 11 sets of tap presets that are labeled P0 through P10. The reference receiver equalization scheme for Gen 5 is more elaborate than it was for Gen 4. Rather than the 2-pole 1-0 continuous time linear equalization filter response, PCIe 5 uses a 4-pole 2-0 CTLE filter response. The new CTLE offers greater flexibility and a deeper range of gain, from -5 to -15 decibels in 1 dB steps, as shown here. PCIe 5 also adds a third tap to the reference receiver decision feedback equalizer, the DFE. Here's a schematic, here's a block diagram of the receiver. You can see that the CTLE is an input filter. The clock recovery recovers the clock to position the timing sampling point for the slicer, which is the logic decoder. And the DFE has the 3 taps which are added together with the output of the CTLE for the input to the slicer. All right, that brings us to really the most complicated part of this presentation, link training. There are two types of link training: transmitter link equalization test and receiver link equalization test. Link training is only required for the CEM specification. It's not required for the base specification. Link training is operated through a link training status and state machine, the LTSSM. The state machine configures the system to operate at the maximum data rate possible. In the first phase of the state machine, detect, the receiver detects the transmitted signal. On initial power-up, the transmitter transmits a PCIe Gen 1 signal at 2.5 gigatransfers per second. The second phase, polling, is where the receiver synchronizes with the waveform and determines the bit rate and polarity. The third phase, configuration, the number of PCIe channels is determined, that is, its lane width is determined. In the L0 phase, link training is enabled. In the recovery phase, the transmitter operates with FFE taps set according to a preset or a set of optimized taps from some previous state of operation. On power-up, it operates with all taps set to 1, which is equivalent to not having any feed-forward equalization. PCIe Gen 2 has just 2 presets, Gen 3 has 10, and as we've already commented, both PCIe Gen 4 and Gen 5 have 11 sets of FFE taps. Phase 6. The loopback phase is the crucial phase. The receiver analyzes the bit error rate with some sort of built-in system tests, like a cyclic redundancy check. Of course, different receivers can use different levels of built-in self-test sophistication. If the bit error rate at this state is less than 1 in a trillion, and the system is operating at a rate below PCIe 5, below 32 gigatransfers per second, then the receiver sends a request to the transmitter for a data rate increase. This is equivalent to an increase from one PCIe generation, whatever it's operating at now, to the next generation. The receiver then returns to phase 1, the detect phase. On the other hand, if in the loopback mode, the bit error rate performance is larger than 1 in a trillion, but the link training time has not yet exceeded its maximum, then one or more of the following occurs. The receiver can send a request for a different set of transmitter FFE taps, increment, decrement, leave the taps the same, or load another set of presets. Or the receiver can also modify its own equalization scheme. For example, it could adjust its continuous time linear equalizer gain and or its DFE taps. But remember, PCIe only specifies the receiver's bit error rate performance, not the specific equalization technology. The system then returns to the recovery phase with the new equalization scheme. If the link training time has exceeded its maximum and the receiver has not found an equalization scheme with which it can operate at or better than 1 error in 10 to the 12th bits, or if it loses synchronization, the system then reverts to a lower data rate and operates at that data rate from then on. In the context of transmitter equalization testing, a Burt error detector plays the role of reference receiver operating in loopback mode. It directs the Burt pulse pattern generator, I'll call it a pattern generator most of the time today, to send requests for different presets to the SerDes device under test transmitter. An oscilloscope captures and analyzes all of the transmitted waveforms. In the context of receiver testing, the Burt pattern generator plays the role of reference transmitter. In phase 1, detect, it transmits protocol-based training sequences that convey the bit error, the bit rate, the polarity, and configuration to the SerDes receiver, the SerDes being the device under test. In Phase 5, recovery, the SerDes, now in loopback mode, transmits feed-forward equalization tap requests, and the Burt pattern generator receives and interprets those messages and modifies its FFE scheme accordingly. This diagram shows either base or card electromechanical CEM testing. In a base test, the device under test consists of the SerDes itself mounted to a system board. In the CEM test, the device being tested consists of both the SerDes and the add-in card to which it is mounted. The two tests are quite similar. We'll work through the details of the CEM add-in card test and then describe how this test generalizes to the base test. Transmitter testing is performed with software available from the PCI Special Interest Group, the PCI SIG. The software is called SIG Test, and it must run on the oscilloscope. The Burt pattern generator sends requests to the device under test, the DUT transmitter, through the PCIe physical layer logic subblock protocol. The Burt pattern generator sends requests to the DUT SerDes for every FFE preset at every PCIe data rate. The DUT transmitter modifies its FFE scheme and transmits a signal. The DUT transmitter output is split so that its signal is sent to the oscilloscope, shown here with the green cables, and the Burt error detector, in purple. The error detector, in its role as reference receiver, confirms the preset change. The Burt uses the pattern generator auxiliary output, the black cable, to trigger the oscilloscope acquisition of each signal. The scope captures the waveforms with every FFE preset and every data rate. It then runs SIG test and evaluates every one of the waveforms it's acquired according to the compliance requirements. The transmitter link equalization response test measures the length of time it takes for the DUT transmitter to respond to FFE tap requests and determines whether the response is correct. The Burt pattern generator differential output from the noise module is split so that the signal is transmitted to both the DUT receiver and the oscilloscope. The DUT transmitter output is also split so that its signal is sent to both the oscilloscope and the Burt error detector in its role as reference receiver. The test begins with the Burt pattern generator transmitting a preset request to the DUT transmitter, a negotiation in the phi layer logical subblock. The DUT responds by altering its feed-forward equalizer taps. The oscilloscope also receives and must be capable of identifying the preset request in order to measure the timing of that request, T sub rec. It is in this sense that the oscilloscope must have protocol functionality. The oscilloscope screenshot shown here shows the Burt pattern generator output in gold and the DUT transmitter signal in blue. The time at which the DUT transmitter FFE presets change, T sub change, is obvious, where the blue signal experiences a discontinuity in amplitude. The oscilloscope determines the time of the request by marking the time at which the packet containing the request is received, another example of its protocol functionality. The elapsed time between the timing that the taps change, T sub change, and the timing of the request must be less than or equal to the specified maximum, which is 1 millisecond for the CEM specification or 500 nanoseconds for the base specification. PCIe Generation 5 receivers have only one compliance test at the phi level. The reason for this is that the link training test and the stressed receiver tolerance test are both evaluated at once by using a stressed signal in the link equalization test. The two tests are combined. The Burt pattern generator transmits a test signal that includes jitter and interference impairments, including random jitter, sinusoidal differential mode interference, and sinusoidal common mode interference. A variable ISI test board is used that has several differential trace lengths so that it can apply different amounts of loss and ISI. The idea of stressed receiver tolerance testing is to submit the DUT receiver to the worst-case signal that complies with the specification. Once the link is trained and the transmitter FFE and receiver equalization schemes, both the CTLE and DFE, are optimized, the DUT receiver must, of course, operate at a bit error rate that is better than 1 in a trillion. The Burt pattern generator transmits a signal with interference noise to the variable ISI board. The output of the variable ISI board is connected to the compliance base board, which emulates the worst-case performance of the system board. The test signal propagates across the compliance base board to the CEM connector and up the add-in card to the DUT receiver. Notice that the Burt pattern generator applies jitter to the signal through the reference clock. The DUT transmitter output is then sent to the Burt error detector, which both measures the bit error rate and plays the role of reference receiver for link training. Calibration of the stress signal is an iterative procedure that involves application of signal impairments and optimization of the oscilloscope continuous time linear equalizer. The stress signal must be calibrated for every FFE preset, and every condition must comply with the specification. That's a lot of different signals. The goal is to configure a signal subject to the worst-case intersymbol interference that has the minimum allowed post-equalization I height defined at a bit error rate of 10 to the minus 12, that is EH12, and an I width also defined at a bit error rate of 10 to the minus 12 called EW12. Since the signal is delivered to the CEM connector, the worst-case loss of the add-in card must be emulated in the calibration procedure, as you'll see in a minute. This is where things begin to get sticky. The jitter and noise calibration setup begins here. Calibration consists of determining the worst-case combination of random jitter, sinusoidal jitter, and differential mode and common mode interference. It is a complicated iterative process. So let's go through each of the 7 steps carefully. Step 1, we calibrate the worst-case jitter. We connect the Burt pattern generator to the oscilloscope, directly to the oscilloscope, and confirm that the pattern generator applies the required level of RMS random jitter and the maximum amplitude of sinusoidal jitter. In step 2, to calibrate the common mode and differential mode interference, connect the Burt pattern generator output to the highest loss, that is, the longest trace of their variable ISI test board, the compliant 37 decibel channel. Transmit sinusoidal differential mode and common mode interference with amplitudes of 5 to 30 millivolts at 2.1 gigahertz across the test board and to the oscilloscope. Since the channel has about 6 decibels loss at 2.1 gigahertz, the interference amplitude at the Burt pattern generator output will not be the same as that on the signal delivered to the compliance baseboard. In step 3, optimize the oscilloscope continuous time linear equalizer for every transmitter FFE preset, all 11 of them. The unimpaired Burt pattern generator output is transmitted to the worst case 37 decibel channel on the variable ISI board as shown here. The output of the variable ISI board is then connected to the compliance baseboard. The output of the compliance baseboard is connected to the 9 decibel loss channel of the variable ISI board in order to emulate the add-in card's worst-case loss. The 9 dB channel output is connected to the oscilloscope input. Now measure I height and I width defined at 10 to the minus 12. If either is smaller than its minimum allowed value, try another trace on the variable ISI board. Continue trying different traces until you determine the ISI board trace that gives the smallest combination of both I height and I width that is above their specified minimums. Once that's done, in step 4, determine the optimal Burt pattern generator FFE preset and the corresponding CTLE gain of the oscilloscope. For each preset value, the scope should capture at least 5 repetitions of the waveform. The oscilloscope should be capable of determining the optimal CTLE gain automatically. The optimal preset is the one that, combined with its corresponding optimal CTLE gain, gives the largest I height and I width. Step 5. With the optimal FFE and CTLE gain combination, increase the channel loss on the variable ISI board, as in step 3, until you find the smallest combination of both I height and I width above their specified minimums. And now, re-optimize the equalization scheme. At this point, we have a signal with maximum loss, optimal FFE preset, and optimal CTLE gain. Finally, in step 6, we add the differential mode and common mode interference and sinusoidal jitter until the I height and I width are as close to their minimums as possible, and it won't take much. The stressed eye is now, at last, calibrated. Once the Burt pattern generator in its role as reference transmitter is configured and calibrated with worst-case stress and optimized FFE taps, the receiver link equalization test is comparatively easy. The DUT SerDes follows the link training status and state machine that we worked through earlier. The DUT receiver detects the transmitted signal from the Burt pattern generator and should go into loopback mode. Once in loopback mode, the DUT transmitter requests FFE presets of the Burt pattern generator, again in its role as reference transmitter. The DUT then works through the state machine, optimizing link equalization by modifying its receiver equalization scheme as it auditions different Burt pattern generator FFE presets. The Burt error detector monitors the bit error rate through the process. The bit error rate test itself takes about a minute, enough time for PCIe Gen 5 to transmit about 2 trillion bits. Since PCIe 5 specifies receiver performance but not equalization technology, it's possible for the final presets to differ from those obtained during calibration. The DUT is PCIe 5 compliant if its bit error rate is less than 10 to the minus 12. The ability to identify the transitions between state machine states and the timing at which they occur helps identify the DUT failure points. The Anritsu MP1900A bit error rate tester logs the negotiation process between the DUT SerDes and the Burt reference transmitter. Should the DUT fail any step in the receiver link equalization test, you can determine why it failed by analyzing the link training status and state machine training log. This brings us to the transmitter phase lock loop bandwidth test. And after link training, the rest of them will be straightforward. PCIe Gen 5 transmitters operate with a 100 MHz reference clock, the ref clock. A PLL is used to multiply the reference clock up to the data rate. The data rate clock is used by the serializer to latch lower rate data into a PCIe compliant high-speed serial data signal. The phase lock loop bandwidth test measures the DUT transmitter jitter transfer function. That is, the reference clock jitter that makes its way onto transmitted signals. The test is performed by using the Burt subrate clock output to apply sinusoidal jitter to the DUT reference clock. An oscilloscope is used to calibrate the applied sinusoidal jitter amplitudes at frequencies that span the phase lock loop roll-off. The idea is to apply calibrated amplitudes of sinusoidal jitter at frequencies that span the specified PLL roll-off frequency and measure the DUT transmitter output jitter. The jittered subrate clock is connected to the PCIe reference clock signal on the compliance baseboard. The DUT transmitter output is connected to the oscilloscope. The oscilloscope measures the output periodic jitter amplitude for each frequency of applied sinusoidal jitter. PCIe Gen 5 specifies the allowed range of frequencies in which the -3 dB roll-off must occur, as shown here in the blue, and the allowed range of peak jitter amplitudes, as shown in the green of this diagram. The jitter tolerance test, JTOL, is the receiver complement to the transmitter phase lock loop bandwidth test. JTOL is not required by the PCIe Generation 5 specification, but it is an excellent way to evaluate a receiver's ability to tolerate different amplitudes and frequencies of jitter. It's also a fairly fast and automatic test. The stress signal is, again, the worst case but compliant signal, complete with intersymbol interference, random jitter, differential mode, and common mode interference, complete with the optimized combination of Burt pattern generator, FFE presets, and oscilloscope reference receiver CTLE gain. As a debug technique or performance margin analysis, JTOL can be tested with any equalization scheme. Sinusoidal jitter is then added to the signal according to this amplitude frequency template. High amplitude jitter is applied at low frequencies and low amplitude jitter at high frequencies. The roll-off from 1 MHz to 10 MHz follows the specified clock recovery frequency response. In the JTOL test, the Burt error detector measures the bit error rate across the template of sinusoidal jitter amplitudes and frequencies. DUT receivers should adhere to the bit error rate operation limit of 1 in 10 to the 12 for all amplitude frequency pairs. To make the measurement in a reasonable length of time, the bit error rate is usually measured down to bit error rates of 1 in a million, and then the slope of the bit error rate probability is extrapolated to assure that the operational bit error rate is better than 1 in a trillion. The discussion to this point has centered on add-in card testing according to the PCIe Generation 5 card electromechanical specification. The tests for add-in cards are a superset of the base specification tests. Base compliance requires the stressed receiver tolerance test, but does not require either of the link equalization tests. The stressed eye calibration procedure is the same as before, but where the CEM add-in card was tested at the connector to the baseboard, the base test is performed at the pins of the SerDes, the device under test. The PCI SIG provides breakout test boards for base SerDes testing. The breakout boards have two channels, a breakout channel for the device under test and a replica channel that enables calibration of the stress signal at the DUT receiver pins. Notice that the connection is to the replica channel for calibration. The test setup is shown here for base testing. Notice that the 100 MHz reference clock is synthesized by the Burt. The DUT receiver must, of course, perform with a bit error rate of 1 in a trillion or better under the stressed eye conditions. As we've seen, the PCIe 5.0 physical layer tests require an advanced bit error rate tester and an oscilloscope, both capable of emulating the PHY layer behavior of the SerDes. The minimum requirements for the oscilloscope are listed here. It's a wide bandwidth scope that can operate standard serial data analysis software and also has the ability to run PCI SIG test software analysis tools. The minimum bit error rate tester requirements are, first, multiple NRZ pattern generating channels and error detectors that operate at, of course, 32 gigabits per second, 32 gigatransfers per second in PCIe parlance. The Anritsu MP1900A provides up to 16 NRZ channels adjustable from 2.4 to 32.1 gigabits per second each. Since PCIe 5 permits a maximum of 16 channels, the MP1900A accommodates every SerDes channel at once. The MP1900A also has PAM4 ability at 64 gigatransfers per second, which corresponds to 32 gigabaud of PAM4, so you're already covered for PCIe Gen 6. Instrument quality intrinsic jitter and fast rise-fall times are also necessary. The MP1900A typically has 115 femtoseconds RMS jitter and 12 picosecond 20 to 80% rise-fall times. The pattern generators must be capable of applying 3-tap FFE. The MP1900A provides up to 10 taps of FFE, with each tap adjustable from minus 20 to 20 decibels. The error detectors must have integrated continuous time linear equalizers and clock recovery circuits. And as mentioned several times, the Burt pattern generator and error detectors must have protocol awareness at the PCIe PHY logical subblock capable of responding to and initiating link training status and state machine commands. The Burt pulse pattern generators, the transmitter end, must be able to apply all required levels of calibrated jitter and noise in their roles as reference transmitters. The Anritsu MP1900A pulse pattern generators can apply every required signal impairment and a few more in amplitude ranges that exceed those required by the PCIe Generation 5 specifications, including random jitter with an amplitude from 0 to half of a unit interval peak to peak at a bandwidth from 10 kilohertz to 1 gigahertz, sinusoidal jitter at amplitudes from 0 to as high as 2,000 unit intervals, at modulation frequencies up to 250 megahertz. It can also apply a second tone of sinusoidal jitter. Spread spectrum clocking at modulation frequencies from 28 to 37 kilohertz and amplitudes from 0 to 7,000 parts per million. Sinusoidal differential mode interference and common mode interference over a wide choice of frequencies and amplitudes. It can apply white noise with 10 gigahertz bandwidth and a crest factor larger than 5. It can apply bounded uncorrelated jitter, budge, using all the standard PRBS patterns, half period even odd jitter. It can apply internal variable intersymbol interference up to 30 to 32 decibels of loss. It can also apply internally variable intersymbol interference with losses up to 30 to 32 decibels. And you can impose almost any jitter you want through an external jitter input that has bandwidth from 10 kilohertz to 1 gigahertz. Thank you for attending our webinar today. We hope you've learned a lot, and we hope you've enjoyed yourself.